Greeting from Texas A&M University. My name is Steve Su. I am honored to be given this opportunity to share some of my thoughts on controlling nonlinear dynamic systems. Let me use this single pendulum example to make a few points. As we all quite familiar with the governing equation as well as the linearized versions, considering using small angle assumptions. Considering the nonlinear governing equation as well as the linearized equation, and then plot their corresponding responses for small angle 5 degree and 2 degree, and overlapping these two responses on top of each other. And we see that initially the error are very small. However, as the system progresses in time, the error grows rapidly with rather significant increasing phase lags with such a difference in phase and phase lag that indicates that they're linearized, and then also the nonlinear versions, they have fundamental differences at the frequency level. Indeed, the linearized pendulum has a fundamental period, which is not a function of angle, theta. However, the nonlinear pendulum is a nonlinear function of the angle is actually the initial conditions. So this implies that the system does not have a definitive oscillation frequency. Indeed, it displayed time varying frequency. In other words, frequency is a function of the angle. Because spectral compositions, frequency response is considered the fundamental signature of any dynamic system. The linearized pendulum is physically and characteristically a different system from the nonlinear pendulum. Controllers derived from linearized model must compensate the linearization error at a huge cost, including at the expenses of more power, compromise performance, and the system's instability. Allow me to make a few arguments. Linearization distort and misinterpret true dynamics. The moment Taylor expansion is employed, stationary dynamics is assumed. Orthonormal eigenvectors, they, as I said, together they span the solution domain of a linear system in which mapping is linear. However, nonlinear systems do not have characteristic eigenvectors because mapping is not linear. Stability study using eigenvalue is applicable only to linear system. To study the state of stability, we will need to come up with something else, to have a different way to characterize the stability of a nonlinear system. Contemporary controlled theory, they share the following. Linearization, they employ linearization, but however, linearization distort the genuine characteristic of nonlinear dynamic, and linearized system is not able to capture the result route to chaos. Modern day control theory, they also ignore time frequency coupling, but from possible theorem, we know that time and frequency, they're coupled. They're the two sides of the same coin. We cannot just attend to just one and then deliberately, intentionally ignore the other one. And also, we're going to see an example that's going to come up later. Chaotic response has a unstable broadband frequency to responses. And in modern day theory, they also feature feedback, but then feedback serves to disturb, perturb the system, and then push the systems toward further instability and even deteriorations. In modern day theory, they also simplifies a few things, including assuming stationarity, and but because root to chaos is non-stationary, so making such assumptions is quite concerning. Let me use this example to demonstrate some of the fundamental features associated with nonlinear response. This is a elastic rotor that has a transverse crack in it, and as the rotor spin, the crack breathes. Okay, the crack opening and closing perturb the systems, and to a point that the system becomes unstable, dynamically unstable. What we're seeing here is on the left is the instantaneous frequency plot, where the horizontal axis represent time, vertical axis represent frequency. As you can see that there are 1, 2, 3 modes in this instant frequency. The first mode has, and as well as the second mode, it has very definitive, relatively well-defined temporal modal structures. Okay, the reason I named it temporal modal structures because as you can see that frequency does not stay at constant, but rather varying above and below 100 Hertz. And so is the second mode. Okay, this variations is above and below about 50 Hertz. And this temporal modal structure experience a major changes at exactly the moment the new mode was born. Okay, so bifurcation is characterized by birth of a new mode and a change of temporal modal structure of existing mode. As dynamic instability deteriorations gets worse, and then there more modes are born, and ultimately this entire time frequency response going to be broadband, as indicated by this instantaneous frequency plot right here. So if we take a projection onto the left, you're going to see that the overall instability response in terms of the frequency is now getting to be broadband. And then not just that, because the oscillations natures of these temporal modal mode. So we see that the frequency spectrum is also changing in time. Now, let me quickly review a few the modern day nonlinear control theory. The first is OGY. With applying OGY, before we get into that, OGY has a major feature is use Jacobian. Okay, but however, Jacobian is in fact a multi-dimensional realization scheme with only the linear terms in the equation being retained. Okay, and then applying the OGY method to control a non-stationary Hannon map, and then we see that with the bifurcation plot on the left corresponds to without the OGY controller turned on. On the right is with the OGY controller turned on. As you can see that OGY method only worked within a rather finite range of the perturbed parameter. And then once the parameter alpha reaches 2.3, and the system becomes highly bifurcated, in other words, become highly nonlinear. The nonlinear, this OGY method is based on Jacobian, so it can only be applied to the proximity of a predetermined fixed point. Next is That's considered the Lyapunov-based control. And this is example on applying Lyapunov-based control to a two duffing oscillator. One is a stationary duffing oscillator. On the right is a non-stationary duffing oscillator. Okay, Lyapunov controller worked well for the stationary oscillator. However, it was not effective in mitigating the dynamic instability for the non-stationary oscillators. And also because Lyapunov control law is found based on heuristic method. They're neither intuitive nor lending themselves to sound physical interpretation. There are also PID control, adaptive control, adaptive PID control, quasi-logic control, model reference adaptive control, feedback linearization control, time delay feedback control, Takagi fuzzy control, nowadays fairly popular sliding mode control, backstepping control. With all these contemporary control theories, they all fail to mitigate dynamic chaos. A priori, knowledge of the system needs to be available for the control theory to be effective. And unfortunately, none of them control both time and frequency response simultaneously. So I wanted to formulate a novel nonlinear control theory that addresses and then retains the fundamental characteristic inherent of all nonlinear systems undergoing root to chaos. A theory that requires no linearization so that the genuine underlying features of the system being considered are preserved, one that is able to restrain time-varying frequency spectrum from becoming broadband, and also one that can identify the dynamic state of the system in real time. And I also want to have the theory to be able to facilitate control in time and frequency domains simultaneously without distorting or misinterpreting the two dynamics. This is example using single-welled, non-stationary duffing oscillators. Just from the bifurcation plots, we identified A, B, C, D, 4 regions. Okay, and then underneath there's the corresponding instantaneous frequency plot associated with the 4 regions identified in the bifurcation plot. As we can see that even when in region A, okay, the frequency is not a constant, but rather slightly oscillating between a small range, okay, and then also displaying a very well-defined temporal modal structures, okay. And then as the system becomes further bifurcated, reaching into D, what we can see is the frequency become frequency response become broadband, and also because all these modes oscillates change varies in time. So what we see here is it also time changing frequency spectrum. So with all that observation made, then we understand that there is some fundamental property for nonlinear dynamics, for nonlinear systems that is experiencing root to chaos. The first is they're sensitive to initial condition and time delay. This implied using feed-forward concept for control. And then I took inspiration from adaptive filter concept. And then the second property is when the dynamic system becomes unstable, as dynamic deteriorate, the deterioration actually occur in both time and frequency domain. This implied the need for addressing the time and frequency together. So I took inspirations from discrete wavelet transform, okay, and then from there to conceive the solutions addressing time and frequency. The third property is non-stationarity. Okay, this implied the need for implementing some sort of online identification features, and I took inspiration from modern-day adaptive control idea. Next, let me quickly give you a really top-level overview of this, what I call wavelet-based non-linear time frequency control theory with local adaptability. Okay, so what we're seeing here is the architecture of this controller, the control theory, and there is a component right over here is the online identification component. And then this second pad over here is for controlling the input. And then wavelet transformation is implemented over here and to decompose a input sequence, input excitation, before it got further updated, modified with the use of filter W2 and W1. This entire structure is actually conceptually similar to FX LMS algorithm. Okay, but most important thing is now with the use of wavelet transform, so all these the input, all these numbers actually got processed in the simultaneous time and frequency domain. And the reason that I called it this entire idea, control idea, I also name it as one that with the local adaptability, because we have a feature built in that allows the controller to be able to update to find the most optimal optimization step size at each and every control steps for system identification. The same with the optimization step size for the input control component. We mathematically derived this criteria right here for mu2, and the entire derivations actually come with 126 equations. And then because this is for controlling nonlinear system, so it's important that we get the W1 and W2 filters coefficients right at exactly the moment when the controller is turned on. Okay, so it's absolutely critical and essential that we get the W2s and W1s coefficients approximately right. And because if we do it properly, get it right, then the control can be rather rapidly converged, and then the control objective can be very quickly obtained. All right, next is to apply the nonlinear control theory to the grazing control of vibro-impact oscillator. As you know, the vibro-impact oscillator, such as this one, is highly discontinuous. It's very difficult to control. Now, using the normalizations to turn the state space variables into its dimensionless form, and now we have this governing equation for this vibro-impact oscillator looking like this. And then we studied the response, the behavior of this oscillators using these parameters value as the input, and then we get the system's response in terms of the phase plot, and this for the uncontrolled results. Without the controller, and you can see that the corresponding time instant frequency response is broadband. It also has many sophisticated oscillating different modes all together. With the controlled target specified to reach a specific frequency as well as the amplitude A, and then so on this oscillator, vibro-Impact oscillator, as is put under control of the nonlinear controller, and it achieved a very rapid conversion to a controlled state, and then with very small error. And then the corresponding instant frequency plot shows that indeed the frequency response was chaotic and time varying broadband, but once it got controlled, then it becomes just one single frequency. All right, and the corresponding phase portrait shows that there is the control the trajectory is actually a limit cycle. And then this right here shows the control results that corresponds to different models with different parameter input. Okay, and these three show the controlled results. And then as we can see that the system response converged to limit cycle. And then what's most interesting is what we're seeing, all these three controlled results, it all demonstrate very well defined fractal structure. All right, second example is to control non-autonomous time-delayed feedback oscillator. The feedback oscillator, this one has many physical implication, but so it has a significant application in engineering. All right, but anyway, this system is nonlinear. It has a cubic term, and then it also has a time delayed, two time delay terms, with one of them is up to the cubic order. So this is a very difficult to be controlled oscillator. Okay, and then with this, using these parameters, and then we study the behavior of this oscillator. Then what we can see that, and also compared the control result with fuzzy controller and the PID controller. This right here shows the corresponding phase portraits, and what we can see is the time frequency controller put the systems under control, and the system eventually they become a limit cycle, but not so with PID and fuzzy. Most interesting things is if we look at the instant frequency plot for the PID and for the fuzzy, okay, where we see that they both carry unrealistically high frequencies in the instant frequency, okay, as opposed to time frequency control. The systems is actually put under control, and then the system behave following the target frequency exactly. But however, not so with fuzzy and PID. And the reason that the both control result has a high frequency in it because the cubic order feedback and also time delay. This feedback itself serves to perturb the system. Okay, and then that action brings about high frequency response. And not just that, these two controllers are able to maintain dynamic stability. All right, as you can see that there is very significant sophisticated temporal modal structures, okay, indicating dynamic instability. The last example is applying nonlinear time frequency control to permanent magnet synchronous motor. PMSM is quite popular. We find it everywhere. We find it in, say, electric car, hybrid cars as well. And then there is nowadays the most popular control scheme for controlling PMSM is field-oriented control, FOC control. So we incorporated time frequency control into FOC structure and then compared to the PI-FOC structures. And we considered two scenarios. The first one is to maintain the constant load, but then and then applied varying switching speed, allow this engage a motor engage in the very rapid switching of speed. Okay, and then the plot on top is corresponds to the PI-FOC control. The below is correspond to nonlinear time frequency FOC, and you can see that time frequency FOC performs significantly better than PI FOC, and also time frequency FOC is able to maintain identical performance in the two scenario of speed switching, switching to the other side to negative, and then switch back, and then these really put the controller design to the stringent test. And then the second case we consider is constant when the motor is maintaining a constant speed, but then with a sudden applied torque load to the motor. And then we can see is PI-FOC restored back to the reference speed a little bit faster than the nonlinear time frequency FOC. However, there are high frequency oscillations in PI-FOC, and then and this oscillation is necessary, indicating that more power is required, and then longer time for the system to reach the steady state. It also has a significant implications on the mechanical side, on the reliability side as well, which we were not going to be getting into. Okay. And then nonlinear time frequency FOC can simultaneously do the speed control as well as position control. This is one of the most important features for nonlinear time frequency FOC. Modern days PMSM controls scheme, they're not able to do simultaneous speed and position control. And FOC, nonlinear time frequency FOC for position control is fast, is robust, and is accurate, as indicated, supported by these two figures. And then lastly, let me share with you a rather extensive, comprehensive experimental validations. So we evaluate nonlinear time frequency FOC against the most popular, the most common PI FOC control, and with the PI FOC equipped with the infinite impulse response filter, and then without IIR filters. Okay, and what we can see that is PI-FOC with or without IIR filter, they all have major overshoot. Okay, and also extended rippling effect, and that says everything about the instability of the motor itself under the control of the PIFOC. However, no such rippling and overshoot observed with nonlinear time frequency FOC. And nonlinear time frequency FOC it also has 94% less current overshoot, and that means it's very stable, and then it does not draw out additional power to ensure stability and then constant speed operation of the motor. All right, and then the second case is when constant speed with varying torque. So the motor speed decreased to around 570 RPM by an externally applied torque load. And then this torque load is applied abruptly and then immediately afterward removed. Okay, and then it shows that the motor speed for the corresponds to nonlinear time frequency FOC is smooth without the oscillation rippling as seen in both the PI FOC control results. Okay, so this indicates that nonlinear time frequency control is highly stable, efficient, accurate, and then when it comes to the power consumptions, it also indicates that it runs on much lower power consumption. All right, and that should conclude my sharing. Thank you very much.